Hello and welcome to yet another video of Cornerstones of Math. In this video, I will solve the following problem from this year's South Korean College Scholastic Ability Test, the test for high school seniors who want to start their college in year 2026. The last 8 problems of this test are from selective subjects, and this is the very last problem of the calculus subject. So let us take a look at it. F of x is a continuous and increasing function on the entire set of real numbers, and its inverse satisfies following conditions. Condition A, 4 times f inverse of x squared is equal to x squared times x squared minus 5 squared if absolute value of x is less than or equal to 1. Condition B, the absolute value of f inverse of x is equal to e to the power of absolute value of x minus 1 plus 1 if absolute value of x is greater than 1. For a real number m, let g of m be the number of points where the line with slope m passing through point 1, 0 meets the curve y equals f of x. If the function g of m is discontinuous at m equals a and m equals b, where b is the larger number, find the value of this lengthy expression, g of a times limit of g of m as m approaching a from the right, plus g of b times ln b divided by b squared. It is given that the limit of ln x over x as x approach infinity is 0, which can be easily proved by L'Hopital's rule. Alright, obviously we have to deal with this part first, where we have to determine what does the graph of f of x look like. Then we can move on to the second part and deal with this oddly defined function g of m. These seemingly complicated conditions a and b allow us to determine the inverse of f of x, and honestly, it is not even that difficult thanks to the special given condition about f of x. That f of x is a continuous and increasing function. What this tells about its inverse is that f inverse of x is also an increasing function. This helps us greatly when determining the mathematical expression for f inverse of x. Let us take a look at condition A. Here, the square of the f inverse is given, and we can find out f inverse of x by taking square root, but there are 2 possibilities. F inverse can be either 1/2 times x squared minus 5 or minus 1/2 times x squared minus 5. Between these 2, we have to pick increasing function. So let us draw the graph of y equals 1/2 x squared minus 5 right here. From the roots of the polynomial, we can determine the intersection points with x-axis. And from the derivative, we can find the values of x where local maximum or local minimum occur, which is when x is equal to plus minus square root of 5 over 3. Therefore, on the interval -1 from 1 given in condition A, the graph decreases. We have to select the increasing function, meaning that we must pick the expression with a minus sign. That is, this graph flipped over the x-axis. So we have this graph between -1 and 1, and there is one more thing I'd like to address, and that is the slope at the endpoint. Using the derivative, we can find out that the slope is 1 at both endpoints. This will be useful later. Next, let us take a look at condition B for the case where absolute value of x is greater than 1. This time, we actually need to do case division twice. First, we remove this absolute value by dividing into 2 cases, x greater than 1 and x less than -1. If x is greater than 1, the exponential part becomes e to the power of x minus 1, and if x is less than -1, the exponential part becomes e to the power of minus x minus 1. Next, we remove this absolute value by taking either plus sign or minus sign on the entire right-hand side, which again gives 2 functions for each interval. So we have to choose increasing functions. And I believe you can figure out how these graphs look like using the combined knowledge of the graphs like e to the power of x and e to the power of minus x, their asymptotes, and their translations along x direction and y direction. In the end, we can find out increasing functions. If x is greater than 1, this is the increasing function, and if x is less than -1, this is the increasing function. So the graph of the inverse looks like this, and just like the previous case, using derivatives, we can calculate the slope at each endpoint, x equals 1 and x equals -1, and you can realize that the slope becomes 1 at both endpoints. If we combine this with the previously obtained result for the middle section, which was -1/2 times x squared minus 5, we obtain this complete expression and complete graph for the inverse of f of x. We have already found out that in the middle section, the slope of the graph also approaches 1 when x approaches the boundary points x equals ±1. Therefore, we can say that our inverse function is differentiable everywhere. That is, no abrupt change of the slope. Now that we have the entire graph as well as the mathematical expression of f inverse of x, let us now move on to the next part and take a look at the definition of g of m. G of m is defined as the number of points where the line with slope m passing through point 1, 0 meets the curve y equals f of x. So we need to draw the graph of y equals f of x. You can draw this graph by using the fact that the function and its inverse are symmetric with respect to line y equals x. But you know what? I am not even going to draw the graph of y equals f of x in this video, because we can work this out using the already obtained graph of y equals f inverse of x without drawing the additional graph. You see, instead of flipping the graph over the line y equals x, we can instead flip the coordinate axis over y equals x, which is equivalent to considering this axis as the new x-axis and this axis as the new y-axis. I will use capital letters to distinguish them from the original axis. Then the already drawn graph of the inverse can be considered as the graph of y equals f of x from the perspective of newly introduced coordinate axis. And let us think about g of m in this setting. Point 1, 0 from the original function's perspective, that is the capital letter axis, is point 0, 1 in the inverse function's coordinate system, that is the lowercase letter axis. So we are going to consider the lines that pass through this point. As for the slope, this is the direction where the slope m is 0, in the new axis, and this is the direction where the slope is infinity. As for the arbitrary slope m in the capital XY axis, we can consider this as slope 1 over m in small xy axis. In this problem, we have to find 2 points A and B where g of m is discontinuous. So let us try to obtain entire g of m versus m plot. To do that, we must slowly increase the slope m and see what happens. And by the way, from the perspective of the original function y equals f of x, this is the increasing direction of the slope. So first, let us start with the case where the slope m is negative. It is clear that the blue line and the curve meet at only one point, hence g of m equals 1 in this region. This trend goes on for some time as the slope increases, until we reach m equals 0. When m is equal to 0, there is still only one intersection point, hence the value of g of m at m equals 0 is still 1. Now, what will happen to the number of intersection points if the slope increases from here? Well, this is the case where the slope is increased by a slight amount. How many intersection points are there? Well, we have intersection points here, here, and that's it? Well, no, because we also have an intersection points up there, because f inverse of x is an exponential function, which eventually catches up any polynomial functions. By the way, this has to do with the limit given in the problem, which implies that the linear function increases much faster than the logarithmic function. This information may be useful if we are using the original function, which is in logarithmic form. However, we are currently using inverse function, which is in exponential form. If we substitute ln x as y, then we have this limit, which implies that the exponential function increases much faster than the linear function, hence the intersection point way up there. So the value of g of m jumps to 3. So now the number of intersection points is 3, and can you figure out when does this number change again? Well, at this point, right? That is when the line becomes tangent to the curve at negative small x region. This is kind of a special case, so let us denote the slope in this case as m1. So when the slope is m1, at how many points do the line and the curve meet? At here, and way up over there, right? Therefore, at m equals m1, the value of g of m drops to 2. Let us keep increasing the slope. After the slope is increased a bit more, the line cannot meet the curve on negative small x region, and only meets the curve at a single point on positive small x region. Therefore, after m equals m1, g of m drops to 1, and it stays at that value even if m keeps increasing. Now, some of you may wonder what would happen in this special case, where the line passes through the point 1, 2, which is the inflection point of the curve, by the way. This is the case of m equals 1. But you can easily notice that the number of intersection points stays at 1 and doesn't change when the line rotates through this case. So the value of g of m does not change around m equals 1. So now we have obtained the entire graph of g of m. Since g of m is discontinuous at m equals a and b, this means that a equals 0, that is this point, and b equals m1, this point. In the end, we must do some calculations involving a and b, so let us try to obtain the value of b, which is m1, which is for the tangent case. So we have the tangent case here, with m equals b, which was previously written as m1. We are going to think on small xy coordinate system, that is, in terms of the inverse function, because the inverse function is in an exponential form, which is easier to take derivative compared to logarithmic functions. So we have this function on x less than negative 1. This is the case of tangent being drawn from a point that is not on the curve, and you may have learned what to do in this case in your calculus course. First, we let alpha be the x-coordinate of the point of tangency, which gives the y-coordinate minus e to the power of minus alpha minus 1 minus 1. We need to calculate the slope, so we take the derivative, which is e to the power of minus x minus 1, and from here we can use multiple conditions. First, the slope value m is b, but m is a slope from the original function's perspective, that is, in capital XY axis. Therefore, in small xy axis, the slope is 1 over b. This means that e to the power of minus alpha minus 1 equals 1 over b. We can go in two directions from here. We can either solve for b to obtain b is equal to e to the power of alpha plus 1, or we can solve for alpha to obtain alpha equals ln b minus 1. The second thing we can do is to obtain the equation of the tangent, which is y minus the y-coordinate minus e to the power of minus alpha minus 1 minus 1 equals the slope e to the power of minus alpha minus 1 times x minus alpha. we use the fact that this line passes through the point 0, 1. Substituting x equals 0 and y equals 1 gives 1 plus e to the power of minus alpha minus 1 plus 1 equals minus alpha times e to the power of minus alpha minus 1. So if we move everything to the left-hand side and rearrange, we obtain 2 plus 1 plus alpha times e to the power of minus alpha minus 1 equals 0, which is the form where we can use both of these obtained results. So 1 plus alpha is equal to ln b, and e to the power of minus alpha minus 1 is equal to 1 over b. Hence we have 2 plus ln b over b equals 0, which gives ln b over b equals negative 2, and this was in the final expression that we must calculate, which was this expression. Here a equals 0, and we just obtained this. So first, if we substitute a with 0, we have g of 0 times limit of g of m as m approaches 0 from the right, plus g of b times ln b over b squared. Here, g of 0 is this value, hence it is 1. Next, the limit of g of m as m approaches 0 from the right, so this limit, which apparently approaches 3, so the value of limit is 3, and next g of b is this value right here, so it is 2, and finally ln b over b is negative 2, so we have negative 2 squared. Therefore, we obtain the answer 11. So that was the last problem of this year's test. And I have already made a video on the last problem of previous year's test, which I think is on a similar difficulty level. So go check that problem by clicking the link to the top left video, and please don't forget to hit that like button if you enjoyed this video. Thank you all for watching, and I will see you in another video.